Hi, and welcome to lesson 23, Weak and Strong Duality, which is the final lesson of this semester. We're going to be closing with this, with some theory, the deepest part of the course really, which has implications in both modeling and algorithms. You'll see that the implications of this in 405, and if you take game theory, you'll actually see it crop up again as well. You'll also see today how it impacts the algorithms, the simplex method that we even use. To start off with, I'm going to do an example, but an example of an abstract problem. Remember, an abstract problem is really a description of an infinite family of problems. It's where one or more of the constants of the problem is parameterized. So what does that mean? Here, we don't know, it is unknown before you instantiate it how many variables and how many constraints there are. Instead, we have these parameters n and m. N is equal to the number of variables. So that's decision variables. M is equal to the number of constraints. Okay. Aij are going to be the constraint coefficients. Bi are the right-hand sides, Cj are the objective function coefficients. We can write that then in this form A using these. We're maximizing a linear objective. Remember, it's linear over the decision variables. Once you go to solve such a linear program, the C1 through Cn would have to be known, as would the A1 through the Amn and the B1 through Bm. They would all have to be known. And that's what we assume is true when you go to solve this. And then, of course, when you solve it, what you're actually solving for are the unknown decision variables. Okay, so here we have m constraints. They're all less than or equal to constraints, and all the variables are non-negative. If you look at this form over here, this is equivalent to this. And the way in which it's equivalent is you think of the C vector as being just C1 through Cn. The Aij are the components of the matrix. Okay. And then the B vector is equal to B1 through Bm. And the X decision variable vector is equal to X1 down through Xn. Okay. With that in mind, these are the same. These are exactly the same. They're just notationally written with a different notation. Okay, so let's take the dual of this. The dual of this, we're going to have dual variables y1 down to ym, one for each constraint. And we can write our, in the same way that we've done in the past, we can write our Lagrangian form, our Lagrangian inequality. Okay, what is the Lagrangian inequality here? Well, we have the objective. Right. And remember, we're maximizing, so what we want is an upper bound. And the upper bound is going to use these inequalities multiplied by the dual variables. So it'll be y1 times a11 x1 plus a1n xn plus, and then the last one, ym, a m1 x1 plus a mn xn. Okay, that's less than or equal to b, and that's going to be less than or equal to the b1 y1 plus let's be a little careful here. remember what we want to write is that this is equal to the rearrangement of terms. And so what I do is I think of x1 now being multiplied. And I'm going to write it so that I collect all the x1s in each of these, and I think about, well, what is that going to be? And essentially what it is it's summing the y1 through ym's, each multiplied by the aij's, where now it's the first index which is varying, and the last index which stays the same, right? So the last index is associated with x1. The first index is associated with which y's. So here it's going to be, we can see it's y1, a11. Write that carefully. Plus y2, a21, plus dot dot dot, plus am1, ym, and that's all multiplied by x1. And the same is true in between until finally we get to a1, I'm sorry, a1, what am I doing? y1, am, a1n. I'm getting confused. There you go. a1n plus y2, a2n, plus dot dot dot, plus amn, xn, yn, amn. That's all multiplied by xn. Okay, so let me review that because I made some typos along the way and had to erase. The first index of the aij is associated with the y's. The second index of the aij's is associated with the x's. So that's why all of these second indices in that first term are 1, because they are multiplied by x1. And all of the second indices in the very last term are n, because they're all multiplied by xn. And within the summation, you can see the different y's are accruing because of the first index. That pattern is also true in this expression here, of course. I mean, it would have to be true. The first index of aij corresponds to yi. The second index corresponds to xj. Okay, and so what I want to enforce, remember, is that this is all less than or equal to y1 b1 plus y2 b2 plus dot 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 plus y m b m. Okay, and now I can use, some of you in EI, I've been using this expression that I think of this as the first term, this is the second term, this is the third term, and this is the fourth term. So the first term is the objective in the primal. The second term here, I think of this as the dual variables multiplied by the primal constraints. And the third term is the primal variables multiplied, I'm using abbreviations here liberally, by the dual constraints. And the fourth is the dual objective. This is maximizing, so we're looking at, and we're maximizing in the primal, so we're looking for an upper bound in the dual, which we will be minimizing. So immediately I can write out for my dual expression the fact that we're minimizing this dual objective. We're minimizing 4. And it's subject to our constraints. Now, we have to get the constraints. Remember, the way in which we're going to derive this is we know that all of the constraints, well, what expressions do we use? We want the dual constraints, so we should be using equation 3 and equation 1, or term 3, I'm sorry, and term 1, which is the primal objective and the primal variables multiplied by the dual constraints. Remember, in the primal variables, all the xj here are non-negative, okay? So what does that mean? That means that in order to enforce this first less than or equal to, that 1 is less than or equal to 2, which is equal to 3, that means that the primal variables do not change the direction of that inequality when we remove them. Because remember, it's being multiplied by a non-negative quantity. x1 through xn are all non-negative, which means I just write down the term multiplied by each of these variables. So the first one is y1, a11, plus y2, a21, plus dot, 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 plus am1. And I preserve that inequality. It's preserved, so this is greater or equal to C1. Okay, and that's because x1 is non-negative. Okay, and that's true throughout, right? The next one is just going to be, it's the same pattern. Oops, of course I can't forget the ym here. It'll be y1, a12, plus y2, a22, plus dot, 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 plus ym, am2 is greater or equal to c2. That's because x2 is greater or equal to 0. And of course, this is true for all the variables. You see, when we write these abstract models, it really helps us to have a consistent form. What's interesting about this form is that it turns out that any linear program, just like it can be written in canonical form, it can also be written in this form that we have for the primal, using similar tricks. It's beyond scope to worry about that right now, but it's a good fact to know. Okay. And you know what I just did? We don't have m of these, we have n of these. Okay. This is greater than or equal to Cn, and Xn is greater or equal to 0. Okay, so that's how we got the right direction of the inequality for the dual. I will note that we use 2 and 4 to get the correct, we use the primal constraints and what we know they satisfy, which is in term 2, and we use 4 for the inequality we're trying to enforce in order to get the correct bounds on the dual variables. And of course, if you look up here, we know that each of these constraints are less than or equal to already, so we want to keep them going that way. We don't have any equalities, and we don't have something completely restrictive. We have less than or equal to, and we have no greater or equal to. So they're all going to work in the same way, and they're working in the right direction. So we want to keep them that way. So we don't want to allow them to get changed. So we keep all of these non-negative as well. Okay, so it's y1 through ym are all non-negative. Okay, so if you have any questions about how this is done, this is definitely a good time to attend the EEI and ask me. I'm now going to rewrite this in this linear algebraic form using the understanding from here. And we're going to see that the dual can also be written, well, let's just minimize y transpose b, and let's write these as vectors. Y vector transpose b vector, and it's subject to y transpose A is greater or equal to C transpose, and Y is non-negative. Okay, now you might be saying, wait a second, you put the variables on a different side as before, and you use a transpose for C transpose, and that's just making sure the linear algebra is written correctly. I did that because of what we're going to do next. Note that y transpose A is a left multiplication of a vector times a matrix, and that results in a row vector, which is why I so C transpose, because C I had defined as a column vector. So it's just making sure that everything lines up correctly. Now I'm going to stop here, and I'd like you to